Now what I want to do is actually go through the process of calculating a between subjects one-way ANOVA. So we're going to go through the process of hypothesis testing, and the example that we're going to use is looking at associations between educational attainment and your age at the birth of your first child. So we're asking, is there an association between how much education you get and how old you are when you give birth? And so, to answer this question, let's say you have a group of researchers and they interview 10 mothers and they gather data on how much education they have and on how old they were when they have their first kids. And so, based on this, we group our mothers into three categories. So, we have one factor, educational attainment, and it has three levels or categories. So, you can have a high school diploma or less, bachelor's degree, or master's degree or higher. Let's say this is what our data look like. So we have one group that has a master's degree or higher, one group that has a bachelor's degree, and one group that has a high school diploma or less. Remember, we have 10 women in our sample because we interviewed 10 mothers, and we asked each of them for the age at birth of their first child. So for the master's degree folks, they told us their ages were 30, 31, and 32. Bachelor's degree, we had 4 people in that category, and these are their ages. And then for high school diploma or less, we had 3 people in that category, and these are their ages. So we can do a few things here. First of all, we can come up with the sum of ages for each group. So if we add up the ages for the master's degree group, we get a sum of 93. We can do the same thing for the bachelor's degree group. We add up these 4 ages, we get 112. And then we do the same thing for the high school diploma or less group. We add up these ages and we get 75. And then we have N, which is our sample size for each of these groups. So we have 3 people in the master's degree group, 4 people in the bachelor's degree or higher group, and then 3 people in the high school diploma or less group. So this is our sample size. We could also take the mean of each group. So we're just taking the average age across the 3 groups. So for the master's degree, their mean age is 31. Bachelor's, their mean is 28. High school diploma or less, their mean is 25. And then we can calculate a sample standard deviation for each of our groups. This tells us how much variability we see in age within the 3 groups. And so we have a sample standard deviation for each of our 3 groups. Now let us graph the raw data that we just described. So we have age at birth of our first child, and we have 3 groups. We have our master's degree group, our bachelor's degree group, and our high school group. And so if we just look at this raw data pretty quickly, we see that the mean age for the master's degree group is 31, for the bachelor's degree group is 28, and for the high school diploma or less group is 25. So if we were just going to eyeball this quickly, it looks as though as education goes up, the age at birth of first child also seems to go up. Or another way to think about it is that you see a decrease in age at birth of first child as education goes down. But it doesn't look like it's a huge effect. We see some differences, but we also have to figure out, are those differences meaningful? Are they actually statistically significant differences based on education? And so that's what we're going to use our hypothesis testing to determine. Step one in hypothesis testing is always to pick our test. And so here we're comparing the means of 3 independent samples. We have one factor or independent variable, and that's education. And that independent variable or factor has 3 levels. We have high school diploma or less, bachelor's, and then master's. And then the dependent variable we're interested in is age at birth of first child. And so since we have 3 independent samples, we can't use the independent samples t-test because that only allows for 2 different groups. We have 3 groups, however, and we're looking at the means of 3 independent samples instead of 2. So we have to do an ANOVA. So again, it's between subjects. We're comparing 3 different groups. It's one way because we only have one independent variable, and that's educational attainment. So we're going to use a between subjects one-way ANOVA in this example. All right, so now it's time to check our assumptions. So the assumptions that we have here is that we're assuming our data come from random samples. Let's assume that's true. We assume independence of cases. So we're going to assume that the people in the master's degree group don't have any relationship to the people in the bachelor's degree group, and they also don't have relationships to the people in the high school group. So it looks as though we have independence of cases. And we're going to assume normality. We're going to assume that our ages follow a normal distribution. And then that fourth assumption is going to be that homogeneity of variance. And remember, that has to do with the standard deviation and how much difference you see in standard deviations across groups. So if we look at our three groups, we see the standard deviations are pretty close. They're all hovering pretty close to 1. So you have similar amounts of variability within your three groups. So it looks like our data passed the assumptions of this test. Now it's time for us to list our hypotheses. And when we do ANOVA, unlike some of the other tests that we did where we have one-sided or one-tailed or two-sided or two-tailed test, we always do two-tailed test here. We never have directional hypotheses when we're talking about ANOVA. So our null hypothesis is going to say that the means of our three groups are the same. So mean 1 is equal to mean 2, which is equal to mean 3. Our alternative hypothesis is going to say at least one of the population means is different from the others. We don't know which one, so we're not making predictions about which one is different. At this point, all we're saying is that at least one of the means is different from the others. Now it's time for our next step, which involves setting our decision rule. So with our previous test, what we did was calculate a critical value of t and then compare that to some test statistic t, and we used that to decide whether or not to reject the null hypothesis. With ANOVA, we're not calculating a critical value of t. This time we're calculating the critical value of f, and that represents our F ratio. We're going to take that critical value of f and then compare it to a test statistic f, which I'll show you how to calculate. And then the critical value of f helps us to determine the common zone versus the rare zone, just as we've seen in our previous test. So if our test statistic f falls in the rare zone, meaning that it's greater than the critical value of f, we know that that means we're going to reject our null hypothesis, because it's very rare that we would get a test statistic like that if the null hypothesis is true. If we find, on the other hand, that our test statistic f is less than our critical value of f, we know then that we're not going to reject the null hypothesis. So this is our decision rule. We come up with the critical value of f. We're going to compare it to a test statistic f, and we use that to decide whether or not to reject the null. To determine our critical value of f, basically what we first need to do is determine our degrees of freedom. And so there are three different types of degrees of freedom when we're talking about the critical value of f. There's a between subjects degrees of freedom, a within subjects degrees of freedom, and then total degrees of freedom. So the degrees of freedom between subjects is equal to k minus 1, where k is the number of groups that you have. So here we have three groups, high school or less, bachelor's, and master's or higher. So here k is equal to 3. And so our between subjects degrees of freedom is going to be equal to k minus 1, which is the same as 3 minus 1, which is going to be equal to 2. Next, we need to determine our within subjects degrees of freedom, and that's going to be equal to n minus k, where n is the total number of participants in our study, and in our example, we have 10 participants, and again, k is the total number of groups we have. Here we have 3 groups, so k is going to be equal to 3. So our within subjects degrees of freedom is going to be equal to 10 minus 3, which is 7. And then finally, our total degrees of freedom is going to be equal to n minus 1, where again, n is the number of participants in our study. Here it's 10, minus 1, which is going to be equal to 9. So between subjects degrees of freedom is 2, within subjects degrees of freedom is 7, and then the total degrees of freedom is 9. And so we can use these values to figure out the critical value of F. And in your textbook, there's actually a table. It's an appendix in table 4, and that has the values that we need to calculate the critical value of F. And basically that critical value, you're going to be able to calculate that by looking at the intersection between the between subjects degrees of freedom, which is going to be our numerator, and then our within subjects degrees of freedom, which will be our denominator. And I'll show you an example. So just to review the terminology again, we have our between subjects degrees of freedom are going to be equal to k minus 1, where k corresponds to the number of groups we have. Our within subjects degrees of freedom is going to be n minus k, where n is the total number of participants and k is the total number of groups we have. And then the degrees of freedom total is going to be n minus 1, where n is the total number of cases we have minus 1. Okay, so here we have Appendix Table 4 from your textbook, and it gives us the critical values of F based on our within subjects degrees of freedom and our between subjects degrees of freedom. So to determine the critical value of F, we look at the denominator degrees of freedom and the numerator degrees of freedom. So the denominator degrees of freedom are in this left column here, and that corresponds to the within subjects degrees of freedom. So in the previous slide, we said that the within subjects degrees of freedom was 7. And then here up top, we have the numerator degrees of freedom. And that's going to be the between subjects degrees of freedom. So we just calculated that the between subjects degrees of freedom was 2. And so we're going to look to see where these two intersect. So we have 7 here in the column and 2 here in this row up top, and they intersect at 4.737. So our critical value of F in this example is 4.737. Okay, so now we know the critical value of F. We said it was 4.737. And so now we're setting our decision rule. So that critical value, remember, tells us the cutoff points for the common zone versus the rare zone. And so we're going to take that critical value of F and we will compare it to a test statistic F. And if that test statistic is in the rare zone, so it's out here, we know that we will reject the null hypothesis. If that test statistic is in the common zone, meaning it's less than 4.737, we know that we won't reject the null hypothesis. All right, so our next step is to calculate our test statistic F. And there's actually a lot of math involved in calculating this F test statistic, but I'm not going to require you to do all of this math. Nowadays, we usually use software to calculate this. And when you do the lab for this section, you'll learn how to do that. But I will generally give you the F test statistic, and I do care about you knowing how to interpret it when I give it to you. And so we'll talk about that next. So if we use software to calculate this F test statistic, we get an F of 31.40. And remember that F test statistic is going to be the ratio of the between subjects variability to the within subjects variability, or the between group variability to the within group variability. And so that F test statistic in this example, again, is 31.40. And that's what we're going to compare to our critical value of F. All right, so now it's time for us to interpret our results, and we have a few questions we want to answer. First, we want to know whether or not we're going to reject the null hypothesis, and that will be determined based on how we compare the critical value of F to the test statistic F. And then just like we did with our other tests, we want to know how big the effect is. And then finally, we want to know where's the effect found. So if you remember before, I told you our hypothesis said that at least one of the means is different from the other two, but we don't know which mean is different. And so that's what we want to figure out. Where is the effect found? So you'll remember that our research question was, is there an association between education and age at birth of first child? And so we had our 3 groups, the master's degree or higher group, the bachelor's degree group, and the high school diploma or less group. And so we calculated a critical value of F equal to 4.737. And we said that we would use that value to determine the cutoff points for the common zone versus the rare zone. And if we found that the test statistic F is greater than that critical value, then we know it's in the rare zone, and so we would reject the null hypothesis. If it's less than that critical value, then we know that test statistic is in the common zone, which means we do not reject the null hypothesis. So we have a critical value of F here of 4.737, and our test statistic F we just calculated was 31.40. And so that's way out here. It's very much in the rare zone. So since our test statistic F is in the rare zone, we know that means that we would reject the null hypothesis here. Okay, so now it's time to put our results in APA format. So in APA format, we start with F. That lets us know that we did an F test, and so that tells us that we did analysis of variance. And then in parentheses, we have the between group degrees of freedom and the within group degrees of freedom. Those are the same values that we use to calculate that critical value of F. And then equals the 31.40 here. This is the value of our test statistic F. And then we have P less than 0.05. The 0.05 tells us what our alpha level was. So we only wanted a 5% chance of making a type 1 error. And then the P less than 0.05 tells us that we rejected the null hypothesis. We know that this test statistic that we got here of 31.40 would be extremely rare if the null hypothesis was true. We have less than a 5% chance of getting a test statistic like this if the null hypothesis is true. And so this is how we would write our results. All right, so now we want to know the size of our effect. And so to determine this, we're going to calculate R squared, which is something that we've calculated with other tests. And R squared tells us how much of the variability in our dependent variable is accounted for by our independent variable. And so if we're using our age at first birth and education example, R squared would tell us how much of the variability in age at birth of first child, which is our dependent variable, how much of that variability is accounted for by the mom's education. And so we have some general rules to decide whether or not our effect size is small, medium, or large. If R squared is less than 9% or 0.09, we consider that to be a small effect. If R squared is between 9% and 24%, we consider that to be a medium effect. And then finally, if R squared is greater than or equal to 25%, we consider that to be a large effect. So let's say I tell you that R squared is equal to 90%. That means that 90% of the variability we see in age at birth of first child is explained by how much education the mom has. And so again, if we're looking at our interpretation of R squared, remember we said that less than 9% was a small effect, 9 to 24% is a medium effect, and greater than or equal to 25% is a large effect. So since our R squared is 90%, we would say that is a large effect. And so if we imagine this box here corresponds to all of the variability we see in age at first birth, 90% of it, which is all of this blue area, is accounted for by education. And then about 10%, which is this kind of pink area, is all of the variability that's not accounted for by the mom's education. So there could be other factors at play. It could be the dad's education that matters. It could be where in the country a person lives. It could be the race of the mom. It could be lots of different things, but we know it's only 10% is accounted for by other factors. And an R square of 90% tells us that 90% of the variability you see in age at birth of first child is accounted for by how much education mom has. All right, so now we want to determine where the effect is. So remember, with our hypothesis test, we said that at least one of the means is different from the other two, but we don't know which mean is different. And so we have to do something called a post hoc test. And the test that we use is called Tukey HSD, where HSD stands for honestly significant difference. Okay, so there's a lot of math involved in calculating the Tukey HSD, and so I won't require you to do that by hand. You'll learn how to do it in SPSS, but I do care about you knowing how to interpret the HSD. And remember, HSD stands for honestly significant difference. And so basically what you'll do is you'll get an HSD value. And if the difference between a pair of means is greater than or equal to that HSD value, then we can conclude that there's a statistically significant difference between the two groups. And I'll show you this in the context of our data. So let's say that when we're looking at our age at birth of first child example, we calculate a Tukey HSD equal to 2.23. That means that any two means that we see that are at least 2.23 different from each other are honestly significantly different from each other. All right, so let's look at our example in the context of this Tukey HSD. So we said that our HSD was 2.23. So that means if we look at our three means, any two of them that differ by at least 2.23 years are honestly significantly different from each other. So given that, which differences are significant? So we can start by just looking at the difference in age based on educational attainment. So if we subtract the mean for the folks who have a master's degree, and we take that minus the mean of the folks who have a bachelor's degree, we get 31 minus 28, which is 3. So the difference between those two means is 3 years. So that would tell us that the difference between master's degree and bachelor's degree is honestly significantly different because it's at least 2.23s, 3 years. We have a distance of 3 years here. Now let's compare our master's mean to our high school diploma mean. So the mean age at birth of first child for the master's degree folks is 31, and the mean age at birth of first child of the high school diploma folks is 25. 31 minus 25 is 6, and so 6 is greater than 2.23. So we know that the difference between these two means is honestly significantly different. And then finally, we can compare the bachelor's degree folks to the high school diploma folks. So the mean age at birth of first child for those who have a bachelor's degree is 28. The mean age at birth of first child of the folks with a high school diploma is 25. And so the difference between those is 3. And again, 3 is greater than 2.23. So that means that the mean age of the folks with bachelor's degrees is honestly significantly different from the mean age of folks who have a high school diploma. So it turns out in our example, all three of these means are honestly significantly different from each other. All right, let's look at another example of how we might calculate and interpret the Tukey's HSD. So let's say we have 90 participants and they're in romantic relationships and they're assigned to one of 3 communication style training groups. So group 1 is taught to communicate in an assertive manner. Group 2 is taught to communicate in a passive manner. And then group 3 is taught to communicate in an aggressive manner. And so we have each of our participants in each of the 3 groups complete a relationship closeness scale where the higher scores indicate that they have greater perceived closeness. All right, so now let's say that the mean closeness score for those in the assertive communication group is 7.0. The mean closeness score for those in the passive communication group is 5.5. And then let's say that the mean relationship closeness score for the people in the aggressive communication group is 5.0. And let's say we do our hypothesis testing and we find that our results of our ANOVA are significant. And we do a post hoc test using Tukey's HSD, and we get that Tukey's HSD is 0.833. And so now the question becomes, which of these means are honestly significantly different from each other? Okay, so we know our Tukey's HSD is 0.833. So that means when we look at the difference between our means, any difference that's greater than 0.833 is going to be an honestly significant difference. That's what the Tukey's HSD tells us. So again, our assertive group has a mean closeness score of 7.0. The passive group has a mean closeness score of 5.5. And the aggressive group has a closeness score of 5.0. So we can determine the difference between these means in order to determine which ones have an honestly significant difference. And so first we're going to look at the mean closeness score for the assertive group minus the mean closeness score for the passive group. So that's just going to be the 7.0 minus 5.5, which is 1.5. And we can clearly see that 1.5 is larger than 0.833. So that tells us that these two groups are honestly significantly different from each other. Now we can compare the assertive group to the aggressive group. So the mean closeness score for the assertive group was 7, for the aggressive group was 5, and so the difference in closeness between those groups is 2. And we know 2 is greater than 0.833, which is our honestly significant different value. So that tells us that the mean closeness scores for the assertive group versus the aggressive group are honestly significantly different from each other. And then finally, we can compare the passive group to the aggressive group. So the passive group has a mean closeness score of 5.5. The aggressive group has a mean closeness score of 5.0. And so when we take the difference between those two, it's 0.5. And you'll notice here that 0.5 is not greater than or equal to our Tukey's HSD value. So that tells us that there is not an honestly significant difference between these two groups. So again, just to review, the assertive group is honestly significantly different from the passive group because the difference in their means is greater than Tukey's HSD. The assertive group is also honestly significantly different from the aggressive group because the difference in their means is 2, which is larger than that Tukey's HSD of 0.833. But when we look at the passive group versus the aggressive group, the passive group and the aggressive group are not honestly significantly different from each other in terms of closeness because the difference in mean closeness here is only 0.5, and that value is less than Tukey's HSD of 0.833. So that's all that we will cover today. Thanks for listening, and please reach out if you have any questions.